Good afternoon, all of you. Are you getting my voice? I'm audible or not? Okay. I'm waiting for some participants. Let them because only 23 are there. Then we will start. So, good afternoon, participants. Actually, today the in the timetable, the lecture was for Dr. Matthew Srinivas from NIT Warangal. But in NIT Warangal, some issue is there related to electric power. So he is unable to at 3 to 5. Okay, so I will arrange at the place of Matthew Srinivas. Wait for a minute. So I think you are getting my voice, and that will start now. If you have any issue, you can message me. Otherwise, you can use your microphone also, because no one is there to manage. So the topic today we will discuss, that is related to dimensionality problem. So the dimensionality problem we will discuss. Today. I think my screen is visible to you. So let me assume here some assumptions we will take, because in machine learning actually the work or the we are doing here, the main is like we are doing the classification. Okay, if we have two classes with us, two classes means one class, like one class maybe of images, so many images may be there, 1,000, 1 lakh, or 10,000, it doesn't matter. Suppose all are dogs images. Second class is there. Okay, and here also we have lot of images or data. Okay, data may be there, and suppose this is related to cats. Okay, so like that we have two classes here. Okay, so now you will get another image from the user, and your program or the your algorithm will identify the image is related to dog, or the image is related to cats, or the images doesn't belong to any class here. Okay, so suppose like that we are having two classes here in my problem, but there may be 1,000 classes, 10, 15, or 20 classes may be there, but that many classes we can't take, for example. Okay, it will create a problem for us. So suppose we have two classes here. Suppose this is one class, that is omega 1. Okay, or you can say for dogs I'm using omega 1, and I have another class also, that is omega 2, or you can say related to cats. So like that I have two classes here, and now you need to identify the which class the image you are taking, to which class it belongs. Okay, so there are various methods to develop. Sometimes we are calculating the probability. In last class, Professor R.B. Subramaniam has discussed this part. So you will calculate the probability of class omega 1, and at the same time you will calculate the probability of class omega 2. And here you will compare the probability of the image you are having, okay, and to suppose it is very near to this one or very near to this one, then you can classify that this particular image is belongs to this class omega 1 or class omega 2, okay. But what will happen, suppose I said that p omega 1 is equal to p omega 2, then it is very difficult because sometimes data may be like that, okay. So these two classes may be overlap with each other like that also. So then we will calculate the variances, okay. So we will calculate the variances, but suppose in that case this is also same, okay. Then it is very difficult actually. The problem here I am discussing this part actually, this part here. So this is the error here because if any particular value is at this place, then it is very easy to identify that this is the class, this point is belonging to omega 1, or any point, suppose it is here at this place, then it is also very easy to identify that it is belongs to class omega 2, okay. But suppose you have a point here or here at this place, because this particular region, this entire region is belonging to omega 1 and omega 2, both the classes are available here. And here it is very difficult to decide actually, you can't take the decision at this place. Decision will be very difficult because it may be belongs to omega 1 or omega 2, okay. And suppose it will overlap more, suppose when we are saying the probability of omega 1 is equal to probability of omega 2, then it will overlap much more here like this, okay. Then it is very difficult to decide, okay. So how you can solve this problem? So the here at the same time, suppose you have different data, so variances may be same, probability may be same, but mean values, mu1, sorry, at the mean values, this mu1 is not equals to mu2, okay. Because this is the property of your data actually, this is not possible. And independent variables are there, okay, and the data is independent, and mu1 is not is equal to mu2, and this value is for mean, that will not be equals to each other. How we can solve this problem? So if the this mean can decide, so how mean will be the different from each other? Suppose we have a data here, suppose I have a data here, okay, and this some data is there with me, and I have only three values, suppose, okay. Suppose here I have some values, some value here, some value here, okay. And when you will calculate the mean for these values, and it will give some value to you. But suppose I at the same time I have 10 values here. So then means in three values, chances are there. Suppose for one data you have three values, for another data also you have three values. Then chances are there that mean will not be separate with each other. Okay, that means separation will not be there. So if you can increase the dimension here, suppose I will take more values at the same time. I have more number of variables, I have more number of data, okay, features actually. The features I am taking more number. Suppose Earlier you are taking three features from dogs, and here also from three features from cats. So now you will take 10 features and 10 features, then this mean will increase actually, and the separation will increase actually, or mean 1 will not be equals to mu 2. Chances will increase that it will not be equals to. Again, suppose you will increase it, you have 100 features here and you have 100 features here. Again, chances will be more separability will be there between mean mu1 and mu2. Okay, so this is the graph here actually. Suppose you have a class omega 1, okay, and you have a class omega 2. So we have the error, this is the error here, okay. So this portion is error, and this is the probability we are calculating for x on omega, okay, and this is the x value, okay. So this is the two class problem here we are discussing. So if somehow we will increase this separation actually here, so then so the graph will be visible like this one and this one. If this, suppose this is class omega 1 and this is class omega 2, then there will be no error actually, because both are separate, totally separate. Separation is proper there, so there is no chance that error will be there. And how you can calculate this portion? Suppose you have a mu1 here, mean value, okay, and this is also mean value, okay. So if the separation is large, then error decrease. If the separation is small, then error will increase, okay. So the features like having apart mean values, then it is easy to classify, okay. If the classification is not up to the mark, then try to make mean apart and add more features in the vectors, okay. Like you increase the more features, then chances are there that classes will be separate, okay. So here actually what I'm saying, if we will add more features, we will add more features in our vectors, we will add more features here, the dimension will increase. Definitely, there should be no doubt in this line. Dimension will increase because earlier, suppose you have three vectors, then it will be 10, and it may be 100, and it may be 1000 also. So dimension will increase. So what exactly we are saying? Adding more number of features, dimension will increase, means we are increasing the dimension for separability here, okay. So this line is totally correct here. Like if you are a computer science person, you can understand that when dimension will increase, that is not good for computational power actually. The dimension will increase, then it is dependent on time complexity directly. It depends, like time complexity will increase. Time complexity means is here the power, the CPU, the GPU, the RAM is required for computational power will increase actually. Okay, and that is also not like you will increase dimensions infinitely. Then computational power will be required and it is impossible to calculate. So that is also a part here. So this portion, when we are saying add more number of features, And I'm saying that add more number of features in your vector, that is very useful for classification. Okay, that is useful for classification. There is no doubt. Okay, but when you are increasing the dimension, that it will increase this portion. Okay, and this problem is called curse of dimensionality. Actually, we are in dilemma situation. If you are not increasing the dimension, then you will go to the like incorrect results will be there. Okay, and if you are increasing the dimensions, then another problem will be there. That problem we will discuss here only, and we will see that what type of problems will be there. But this issue is called curse of dimensionality. If you are not increasing the dimensions, then you will be in trouble. If you are increasing the dimension, again you will be in trouble. So this is the issue here. Okay. So this is called dimensionality problem or curse of dimensionality. Why we are saying that it's a curse of dimensionality? Let me check. Okay. Some mathematical part we will discuss here. Okay. So let me check for computational aspect. So it is like everybody will understand why we are saying this part. So when we are saying mean, actually, so how you will calculate the mean? So mean, when you are calculating the mean, you know very well, you will divide by number of variables or the features available. Okay, and because here it is not like one or two features are there, so many may be there. So k is equal to 1 till n. So that many features are there, and this is the vector x k. So I think everyone will be agree with this formula. So I'm not doing anything extra here. Okay, so this is the formula for mean. So okay, the total number of vectors, the values x1, x2, x3, x4, and divided by number of variables. This is the mean here, and you can check it. Yes. So this is the formula for mean, and directly you can check if k is equal to 10. If k is equal to 10, then it will be work like this: x1 plus x2 plus till x10. Okay, and divided by 10. So it depends on dimension. So what exactly we are saying here? N number of variables, that is like dimension. Okay. So this is also depend, this computational depend on the dimension. Okay, directly. So a vector summation k is equal to 1 to n and division by n. So this is nd. Okay, and directly it is depending on the dimension. And this calculation is always required when we are doing, you are working in data analytics or in data science. This calculation is required. How many number of features are there? Mean you are calculating always. This is also depend on number of dimension. If the dimension will increase, so definitely the computational power will increase here. Second, the very basic calculation is required for data science is covariance. Okay, always. So whatever these calculations are always required actually for the calculation purpose here. So what exactly we are saying here? So what is the formula of covariance? That is 1 divided by n. Sorry. Right. So this is 1 divided by n. Okay, and how you can say right here, so this is k is equal to 1 to n. So there is no doubt in this equation. And how you will calculate the variance x of k means the vector whatever you are having and minus mu I. Okay, and x of k minus mu I and transpose of this one. So when we are doing the calculation in this Python or whatever in the machine learning, we are doing in matrix form. So that's why I'm writing here transpose of this one. Okay. So I means for which vector you are calculating this one. Okay. So that you will take the mean value for that purpose and then the xk for which vector you are doing and you will calculate. So here you can check the multiplication you are doing, okay, with this one, and it will be approximately like n of d square. So when dimension is 3, the calculation is 9. When it is 10, then it will give 100. Means it will increase by this value square. Okay, so this is also depends on the directly on the dimensions. When you are increasing the dimensions, definitely, and covariance is always you are calculating. It doesn't matter for which class you are working. It will be always there. Some calculations are required. Okay, so you will calculate the covariance. Okay, and that will increase the complexity definitely. So I we have proved that this portion, if you are increasing the dimension, the here time complexity will increase, covariance dimensionality will increase. So it will be order of n d square here or d square. Okay, then so these are the basic calculations we are doing. Okay, now how many number of classes are there? So I took two class problem in starting, but suppose you have c number of classes. Okay, mine it may be like 10, 20 or more than 20, 100, more than 100. Okay, so if you have c number of classes, sorry, I will write here. Classes are c. C. Then what will be the complexity? So because 100 classes is there, you need to separate 100 classes. Suppose you have the more dimensions, then it will be directly dependent on c and d square. So number of classes is there, it is also. So increasing the dimensions is not efficient for computations. So that is we have proved here. Okay. So increasing the dimensions or adding the number of features, increasing the dimensions in machine learning, increasing the dimensions is not efficient. Is not efficient because all the calculations are required more power. Okay, more computational power is required. And reducing the dimension again a problem that also you know. What will be the issue if we will decrease the dimension or reduce the dimension? Anyone? So reduce the dimension, reducing the dimension means separability will be less. Will be less. So you need to increase the dimension also. But at the same time, it should be efficient. And that is the issue actually we will discuss here today. in principal component analysis. So what exactly we are doing here? We have the original dimension D, okay, and we will convert into D dash somehow. Okay, these original dimensions may be 100, okay, and we will project these dimensions into 1 or 2 or 3, it depends on the application part. So what exactly we'll do here, the original dimension is D, okay, and we will project these original dimensions on D dash, where D dash is less than or is equal to D. Okay, so it doesn't matter what is the dimension in your problem. So somehow we will reduce these dimensions. There are two methods are there to do this task actually. One is PCA. Through PCA you can do, that is called principal component analysis. Principal component analysis. That we will discuss in detail analysis. And one is also there, that is MDA. We are not going to discuss this one, but it is there for dimensionality reduction. That is called multiple discriminant analysis. NAND analysis. Two methods are there. Okay. So in detail we will discuss PCA only. Okay. But still I will give the idea what exactly we are doing in multiple discriminant analysis. So what exactly we are doing here? What we will try that keeping this mu1 or the mean mu1 and mu2 same not equal, same means whatever it is there in your data, it is not equals to, okay, same, but change the variance, but change the variance, change the variance. So this is the first way you can do it. So what it will give you, okay, change the variance. It will try to reduce the variance and increase the mean. So what it will give you, suppose you have the, this is the one class, okay, and this is the second class. So, okay, this is omega 1 and this is omega 2, okay, and this is probability of x on omega, and this is x here, okay, and this is mu1 and mu2. So here when we are talking about variance, so variance will give you like this value. Sorry, I have done some mistake here. So this mu will be same actually from here, okay, mu2, same values will be there here also, it will be same mu1, okay, but variance will change, okay. Here we are calculating the variances in this case, and you can check that separability will increase here, okay, classes will be separate, okay. So this is the MDA, multiple discriminant analysis we are doing here, okay, and here we are not touching the part of mu, okay, and we will keep same, but we will make the changes in variances somehow, okay. That is detail is there, so we are not going in those details. So let me discuss the principal component analysis. Okay, suppose here in principal component analysis we have n number of feature vectors. And number of feature vectors we have here. Okay, so feature vectors I'm denoting by x1, x2, x3, and xn. So that many feature vectors I have. Okay, each of each feature vector is having a dimension. Some dimension will be there having dimension. The dimension is d in this case. Okay, sorry, this is dimension d. So how you can calculate the mean here? Okay, for this one, so it will be mu or m. You can write 1 divided by n, and k is equal to 1 to n x of k. Simple. So if you have dimension d, so this is the mean. You can calculate with the help of you have the values with you. So what exactly we'll do here in PCA, we will represent this d dimension vector to one dimension vector. Okay, so the purpose here is, so I have d dimension here. So the purpose of PCA is we will try to in PCA, okay, we will represent this d dimensional vector, we will convert into one dimensional vector. So it is available on Python. Direct functions are available. Okay, you can convert it. But here we are not going for that programming part. We will discuss that how it is possible that d-dimensional vector will be converted into one-dimensional vector. So the purpose is to represent this feature vector onto a line somehow. Okay. So when I'm saying this, that I will represent this d-dimensional vector into one-dimensional vector, so the meaning here is I will project all the dimensions or I will project all the vectors onto a line somehow. Okay, let me check how you can do it. If you have any doubt, you can ask me in between. So let me check how you can do it. So suppose we have the vectors here. Okay, we have the vectors here. This is one vector. This is second vector. This is third vector. So many vectors may be there. Okay, I have here some vectors like this, in this. Okay, and here maybe one. Here maybe. Okay, and here maybe. So many vectors I have here. Okay, and I have a line in between. So this is the you have computed actually. We have done this computation. Okay, so this line, the direction of this line is E. Okay, and This is the mean here. Okay, suppose for this person M at this place. So what exactly we are doing here? We will try to project. So these are the vectors for like one class or another class. So somehow I will try. So this is the line you have computed. Okay. So it is passing from this one. This is the median M here. Somehow I will try to project all these points onto this line. So what actually the purpose here is, I will try to project these vector at this position. I will try to project this one. I will try to project this one, this one, this one, this one. So this is the purpose here actually we are doing. So I will project here, I will project here, I will project here. So this is the main purpose actually. The PCA means we have d-dimensional vectors and somehow we will convert into one-dimensional vector in this case. So how you can project? So I will project all the points, all the feature vectors onto a line. Okay. But how you can do it? That is not, so this vector is x. So vector already you have discussed, we have x vector here. So when I want to calculate this line equation of this line, so that will be x is equal to m plus a e. For this one, so this is the e direction, m, and a is here. Oh. So if a is equal to 0, in this case, this is the line. So if a is equal to 0, then you are here at this line. Okay, at this line you are. Suppose a is having some value. A is having some value, then you may be here. Okay, you may be here at this line. Okay, if a is having another value, you may be here. Suppose a is having another value, you may be here. Okay, you may be at this line, you may be at this line. So it depends on the value of a. Okay, if a is 0, then you are on the same line for which you want to calculate. If a is different, so a of k. So this is the value of k actually. We already have discussed. Okay, the k number of feature vectors you are having. So if any feature vector is on this line, then doesn't matter, it is on the same line, no problem. But if any feature is not on the same line, then that is you will represent with a of k. A of k. So like that, it will be there. So if a is not is equal to 0, then moving across the line, okay, in the directions of e only. So we are moving in the direction of. So a represents different points on the line. This one, like x, what will be the equation of this line? X of k, sorry, this is like almost equals to m plus a of k e, means these lines I have drawn here, these lines. Okay, m plus a of k e. So this is the different line here. Okay, so this is the conclusion, like vector xk will represent on the line with the, yes, okay, this is okay. So but when I will represent, so you got it, this is the line, equation of the line you are having. These are different equations here. So this is the line here and this is the line here, and when you want to project at this plane, so this is the error. This is the error. Suppose any point is available at this point and you want to project here, so the error will be there definitely. And this is the error for this point. This is the error here for this point. This is the error for this point. Okay, so how you can handle this error. So first thing is handling error. We will discuss. First is what is the value of this error. Anyone from mathematics background can answer this question. What will be the error in this case? So the error in this case is this is the error directly. Okay. So what you can do here. So this error is like uh, from this line you can separate this line and you will go to the error. Okay. So what you can write here. So I will write in next page. So this is for j of a1, a2, an, and this is the error. And how you can write it? K is equal to 1 to n. Okay, and m plus a of k e minus xk. Okay, because you are reflecting this particular point on xk, the line, and the square of this one. So this is called mean square error actually. This is mean square error. Okay. So what exactly I'm saying here? So I'm saying that this is the line. The equation of this line is x plus m plus a of k e minus you are reflecting at this point, that is xk. Okay. So that is the error here. So how you can write this equation? So I'm writing this equation or rewriting again. So that is k is equal to 1 to n. So what should be the purpose in this case? The purpose is to minimize this error. So a of k e minus x of k minus m and whole square. So I didn't do anything extra here. I took this a of k e, okay, minus x of k minus m. That is also positive. So I have read it in this equation only. So a of k e minus x k minus m. So this is the error in this case. And again, I want to rewrite this equation. So I will use the a plus b square formula here. So I will open this function. So this is like k is equal to 1 to n. Okay. And it will give you a square k. Okay. And e square. This one for this portion. Okay. So I'm taking the mode of this one. Okay. So then plus minus 2 of a of k to a of k e transpose x k minus m. Okay. Plus okay. So this is like x of k minus m whole square. I didn't do anything extra here. So this 2 a of k e transpose this because we are doing the calculations with the help of matrix here. So like that we have written xk minus m and plus we have square this particular value xk minus m whole square. Okay. So now the purpose here to reduce this error. Okay, to reduce the error. So this is the error here. and how you can reduce it. We need to think about it. So if you know about optimization or to minimization, so we will do use here differentiation. So what exactly I will do here? I will to minimize the error, find the derivative. Find the derivatives. Okay, so here I will find the derivative but with respect to a in this case. Okay, so what it will give you? Del j of a. Okay, so when I will divide this portion like this, so you can check here. Yes, at this position 2 of ak, 2 of ak, 2 of ak minus this portion xk minus m, 2 of ak and xk minus ak will give you 1, so it will be 2 e transpose xk minus m and is equal to 0. Xk minus m, there is no a value is there. Okay, so that's why it will it will be 0. Okay, so from here you will get it a of k is equal to e of transpose x of k minus m. So this particular value will be given to you. Okay, one doubt may be there that what about this e? Actually we are not considering this e here. So the reason is I am not taking this e because it's a unit vector. E is a unit vector. Okay, in the direction of line. Because already we have discussed in the direction of line. So what is the value of mod of e is equal to 1. That's why I am not considering this e. Okay. So we have find this a of k is equal to e transpose xk minus k. So ak is nothing but this is the orthogonal projection of xk onto a line in the direction of pi passing through the mean. So this portion we have discussed already. So okay, so this is orthogonal to this line AK. So we are taking the orthogonal projection, okay, of a vector onto a line passing through the centroid. Centroid means this M is there. So which line and which direction will be best? That is the point here. Okay. So we have calculated this portion. So which line or which direction will be best? So which line and which direction will be best? And which direction will be best? Direction will be best. So we will do the calculation for this portion also. So here I was taking for A. So here I will take for E for direction purpose. Okay, but I can't change the error. Error is same here. So I will write the same equation again. A square K mod of E whole square. Okay, minus 2 A of K E transpose x of K minus M plus x of K minus M whole square. Okay, So this is the error we have done already. So here JE is nothing actually. I say is the unit vector in the direction of line. JE is the unit vector in the direction of line. In the direction of line. Okay, so now what you know from this equation actually, from this equation A of k is equal to E transpose xk minus m. So what I will do here, I will replace this E of transpose k minus m, this portion actually, this portion, E of transpose xk minus m. So what I will do here, I will write this equation as it is a square k mod of E square minus 2 a of k, and this portion I will replace with a of k. Okay, already we have proved in last slide a of k, and plus I have this portion x of k minus m whole square. So E is the unit vector. Again, you can convert into 1 that portion. So E is a unit vector. So this is like is equal to here. Same, we are doing the same calculation here. So where it will be 1, so it is a square k minus 2 a square k from here and plus this portion. So minus 2 a square k plus a square k will give you minus a square k and plus x of k minus m whole square. If you have any doubt, you can ask me now. Any problem, any doubt do you have? Okay. So I'm coming within 5 minutes. Please wait.
Okay, sir.
Okay. So yes, so we are here. I told you that I have replaced this particular value with a of k. So here it will give me 2a square k. So I will decrease from this one. So because this portion only I told you it will be equals to 1. So we are not considering in the last, again this portion. So this is the equation we have now. Okay. So now what I will do here again this because I have here a of k is equal to this e of transpose x k minus m. Okay, so what I will do here, I will replace this portion, this particular value with same. Okay, so what it will give you minus okay, so this is e transpose x of k minus m. Sorry, yes, and whole square of this one plus x of k minus m whole square. I think there should be no doubt in this a of k. I am writing here e of t transpose k minus m, and this particular value I have replaced here. E of transpose x k minus m whole square plus x k minus m whole square. So my equation is here, it is minus, this is minus only, and starting e of transpose xk minus m xk minus m transpose key plus x of k minus m whole square. So this is the equation actually we are having here, e of transpose xk minus m whole square plus xk minus m whole square. So this value e of transpose xk minus m I have replaced with this value. Okay. So what is the meaning actually when I am writing this equation? The meaning here is, suppose you want to do, suppose you have matrix 1, 2, 3, and you want to calculate the square of this matrix. So there is two options you can calculate directly. Otherwise, the best method is 1, 2, 3 original, and you will take the transpose 1, 2, 3, and then you can calculate this value. So this square in matrix can be calculated like this. So if you have A is equal to like this, so you can calculate A transpose, and it will give you A of square in the form of matrix. Same thing I have done here. E of transpose xk minus m is the original term. Then I took xk minus m transpose, and then transpose of E, that will be E of transpose, that will be E. So like that I have converted this value here. Okay. Again is E is independent of K. Okay. So we can write like this, minus E of transpose x of k minus m x of k minus m transpose E plus x of k minus m whole square. Okay, so is independent of k here. You can write E is independent of k. Is independent of k because it's a direction actually, and k is the feature vector, number of feature vector. So here actually we have the covariance matrix. So if you know the covariance formula, already we have discussed in starting. Again, I will write it 1 upon n, k is equal to 1 to n, okay, x of k minus m and x of k minus m transpose. This is the covariance formula here. Okay. So if you will check this portion x of k minus m, x of k minus m transpose. So it is like similar. Only this is not there. Okay. So I will not write it, it's a covariance, but I will replace this term here with s. Okay. And this s is called a scatter matrix. Scatter matrix. It's a scatter matrix here, S. So, what will be the situation here? The situation is will be like this, minus E transpose. So, this portion I will replace with S, and this E will be as it is here, E plus x of k minus m whole square. So, this is the equation, my equation here. Okay. So S is a scatter matrix here. It is like similar of covariance matrix. Okay. So let me write it again clearly here. So minus E transpose S E plus x of k minus m whole square. Okay. And this is for JE, the direction you are calculating here. So now, if this is, we are doing all the calculations for error. If you want to minimize JE, okay, to minimize JE, then it is very clear now. So what you will do, you will maximize this E transpose S of E. Why? What's a negative term here? So it will be maximum when JE will decrease anyhow. So to minimize JE, we need to maximize this E transpose S of E. Okay, and then you will go to the correct direction and the correct values for this portion. Okay, for principal component analysis. But how you can do it, this portion? So to maximize this one, so to maximize, we will use some basic mathematics here. We will use one Lagrangian equation is there. And what it will say? It will say E transpose S E minus lambda E transpose E minus 1. Okay, so it is available in mathematics. And if you will take the derivative of this one, derivative of this mu on E. So it is like E transpose and E is E square only. So it will give you 2 of SE. Here also this E transpose and E is E square. It will give you 2 lambda E and is equal to 0. Okay, and from here, so nothing is there now. So you can write again this equation. SE is equal to lambda E. Okay, so this is the eigenvalue expression actually. So here E is the eigenvector. Uh, okay, I will write in next page. Okay, so here I got it as E is equal to lambda E. Okay, so it is eigenvalue expression here actually. Expression here, and here E is eigenvector. Okay, of S, and lambda is eigenvalue. Lambda is eigenvalue. So now from here it is very clear that to maximize this E of lambda E, we need to increase the value of lambda. Okay, so if we will consider only maximum lambda, then n dimensional vector will be one dimensional vector. So okay, so we need to maximize this portion E of lambda E, we need to maximize. Okay, so we need to increase the value of lambda here. Lambda should be maximum in this case. Okay, if lambda is maximum, okay, if you are considering the maximum lambda, then n dimensional vector will be converted into one dimensional vector. And that is the reason actually in principal component analysis, if you have done programming, so we are taking the eigenvalues, eigenvectors maximum. Okay. So here if we consider multiple eigenvalues, okay, actually we have written, so if we will consider only one maximum lambda, then one vector will be. One more statement I need to write here because there will be doubt after some time. If we will consider multiple eigenvalues, okay, be very clear. If you are taking one eigenvalues, then it will be converted into one dimensional. If you are considering multiple eigenvalues, then it will be converted into d dash. Okay, and you will decide that what is how many values you are taking. So if you will take these eigenvalues similar to the dimensions, then it will be equals. If you are taking less than the original dimensions, then it will be less dimension in comparison of the original feature vector. Okay, so this is the principal component analysis. In principal component analysis, we are taking these eigenvalues maximum always. If you have any doubt, you can ask me. We will start, then we will take one example, and then we will tell the Python programming also about this PCA. Any doubt? Get line E. Can you repeat how did you get line E? Okay. Line E, actually, when you have feature vectors, So we are always calculating the planes actually to separate the classes. Suppose you have two classes here, one class here, one class here. Okay, another class at this place. So we need to calculate the plane here actually. Okay, so this calculation will be discussed with you in next lecture, I think. So this plane we are calculating here. So through that we are getting this line actually. So this calculation is always required. Suppose this is class omega 1 and this is class omega 2. Okay, so to separate these classes, we need to draw some hyperplane or plane. Okay, if your dimension is 2 dimension, then it is a plane. If you have more than 3 dimensions, then it is a hyperplane. Okay, so in another directions also. So like that, we need to draw this line actually. So like that, I have drawn this line in between. So it is not like anything difficult here. So this is simple only. You have points at this place, you have points at this place. So somehow we have done this calculation. Okay, we have calculated the margins here, and through those margins we have drawn one line here. Okay, and the direction of this line is E. Okay, and then I will try to project all the points here. So you can consider like it is a graph here. Okay, so you have all the values here reflected at this portion, reflected at this portion, feature values, vectors are, you have all the values, and through these margins you have calculated this line. Okay, and if in next lecture I think I will tell you, if linear regression I will teach, then I will tell you in detail how you can draw this line. Okay, through mathematics only it is possible, like no, the thing is very difficult here. So we have done this portion. Any doubt anywhere else you can ask me, because there should be some doubt actually. Okay, then I will take one example. Because teaching like theory is not very clear sometimes. Okay, so I will take one example in front of you, and then a mathematical example, and then we will see how it will work. Okay, so here I will write compute the PCA of following data. Of following data. So the data is like I have x is equal to 2, 3, 4. I have y is equal to 1, 5, 3. Okay, before explaining this, I want to write some step here how we are doing this PCA. Okay, so step 1, what we will do? We will get the data. Okay, so data is there. Step 2, compute the mean. Compute the mean. Step 3, subtract mean, subtract mean from the data. Okay, you will got it when I will discuss that time. Okay, fourth step, calculate the covariance. Calculate the covariance. You will calculate matrix. Okay, fifth, calculate the eigenvectors. So here you will calculate the eigenvectors. That much mathematics I think everyone knows here. 6 is choose the components. Okay. 7th is driving the new data. Driving the new data. new data. That is the work we will do here. Okay. So I will start from next page. So the data I have here is x is equal to 2, 3, 4. Okay. And y is equal to 1, 5, 3. And this data is for class 1. So I have two classes here. This is my class 1. And for class 2, x is equal to 5, 6, 7,